Hello everyone, welcome to Code Enzyme. This is the 14th video of the series Graph Algorithms for Competitive Programming. And in this video, we will discuss about minimum spanning trees. Now, before starting this video, I would like you to hit that like and subscribe button. And let's start. So before learning about minimum spanning tree, you should understand what a spanning tree is. So let's say we have a graph. Something like this. Okay. So this is a undirected graph. So you can move from here 2 to 1 also and 1 to 2 also. So these are bidirectional edges. And now first we are just discussing what a spanning tree is. So if you run a DFS from this node, so if you run a DFS from node 1, one of the possible way is to go to 2. Then from 2 I may go to 5, I may go to 3, and I may go to 4. Okay, so this is one of the possible spanning trees. Now there is also another possibility that I will start from 1, then I might visit 3 first, and from 3 let's say I visit 5 first, and from 5 let's say I visit 2, and then I visit 4. So this is also a possible spanning tree. um, and you can actually start your DFS from any node. Let's say I start from 4. So if I start from 4, let's say I visit 5 first, then from 5 I go to 2, from 2 I will go to 1, and from 1 I will go to 3. So this is also a spanning tree. So all these are called spanning trees. And you will notice one thing, that spanning trees have n minus 1 edges. So if I have n nodes, all the spanning trees will have n minus 1 edges. So this spanning tree also has n minus 1 edges. So 1 2 3 4 4 edges, 1 2 3 4 4 edges, and 1 2 3 4 4 edges. But the actual graph had 1 2 3 4 5 6 7 edges. So there can be many possible spanning trees. And now let's discuss what is the minimum spanning trees. So let's say we have the same kind of graph, but now these edges are weighted. So every edge has some weight. Let me add some weights here. Okay, so we have an undirected weighted graph, and we want to find a spanning tree such that let's say I have some spanning tree like 1, then we go to 2, then let's say I choose 3. So this has weight 2, this is weight 1, and then let's say I choose 5. So this also has weight 1, and then I think I can choose 3. So this is weight 3. Okay, so this is one of the possible minimum spanning trees, because a minimum spanning tree is that spanning tree whose the sum of the edges in this is minimum. So sum of edges in this graph is minimum. Okay, so if I can minimize the sum of the edges, then this is called the minimum spanning trees. Now there is also an advanced version of this, that we have to find the second minimum spanning tree, the third minimum spanning tree, and so on. But I will cover it in the later section of the series, when we have covered all the standard problems. But for now, let's focus on minimum spanning trees. Now basically we have basically two algorithms to find the minimum spanning trees. One is called the Prim's algorithm, and the second is called Kruskal's algorithm. And I will tell you before only that Kruskal's is important. So basically we use Kruskal's plus DSU to find the minimum spanning trees in competitive programming. Okay, so let's first discuss the Prim's algorithm, because that is not that much important. So let's first discuss the Prim's algorithm. It says we can start from any node, and we can keep expanding the component. And actually this is not the exact definition, but this is just my way of explaining that you can start from any node and you need to keep expanding the component. Let's say we can keep expanding the component by selecting the minimum edges. Right, So let's try to discuss the previous example by Prim's algorithm. So if I want to find the minimum spanning tree using the Prim's algorithm, I will say, let me first erase everything. So let's first consider the so initially all the edges are disjoint for now. So let me have something like okay, and let's say I start with node 5. Okay, so let's say we start with node 5, and node 5 is connected to two edges, this one and this one. Okay, and this has weight, actually three edges, this and this. So this has weight 2, this is weight 1, and this is weight 5. So obviously I should take the so the Prim's algorithm says that you must consider the edge with the minimum weight. So I will use this edge. Okay, and now if I am at 3, I can actually make I will have two more edges. So now I also have to take these two edges into consideration. So I have a 1 and 3. Now I will search in all the yellow edges what is the minimum. So this edge is minimum. So I will consider this edge now. Okay. So I have considered two edges, and now we have two more edges. We have two more edges to consider. One is this edge with weight 2, and one is this edge with weight 3. Right. So now I have to consider the minimum edge, which is yellow. So from this I can say that we can either consider this two. So we have two cases. We can either consider this two, and or we can either consider this two, right? But here is the thing: if you consider this edge, then this will form a cycle, and in a tree there are no cycles, right? So we can't actually consider this case, this two. So I should just remove this two from here, because we are trying to form a spanning tree, and tree doesn't have cycles. So we are only left with the case where we should consider this two. So we will consider this edge with the weight 2, and now we have to consider one more edge, so of the yellow. For edge weight 3, I can't consider this because this will form a cycle now. So I will have to consider this. So the remaining tree, so the minimum spanning tree looks something like this. So in this case, the minimum spanning tree looks something like this. And I just want to tell you, that there can be many possible minimum spanning trees. So this is one of those possibilities. Now for this particular example, there is only one possible minimum spanning trees, but it is not the case that we will always have only one possible spanning tree. Okay, now let's discuss the Kruskal's algorithm. So we have Kruskal's algorithm. Okay, so this says we should this also says that initially all the edges are disjoint. So initially all the nodes are disjoint. Keep joining the weight. Keep joining the nodes with increasing order of weights. So I can say increasing order of weights. Ignore the edge if it so and ignore the edge if it forms a cycle. So ignore the edge if it forms a cycle. Select n-1 such edges. Okay, so this is the algorithm. Let's see for the previous graph how we can go about it. Now what Kruskal's algorithm says is let's say we have something like this. Now let me redraw it again. Okay, so now Kruskal's algorithm says that you have to consider the minimum edges. So I will traverse in all the edges, or maybe I can simply first sort all the edges. Now from the figure that I know I have two possibilities. I can either consider this first edge or this one. So let's consider this edge between 2 and 3. So we will have, so first thing I have considered is this edge. Okay, then the next is this, and it doesn't form a cycle, so I will consider it. Next we have this 2. Okay, so I have two possibilities. I can either consider this 2 or this 2, but if I join this 2 here, it will form a cycle, so I can't actually consider it. So we ignore this edge. Now we see that the next minimum is this one, so I will join it like this. Now the next minimum edge is 3, this 3 and this 3, but I can't consider this 3 because it will form a cycle now. So I will consider this 3, and when I consider this 3, I will have used up all the 4 edges because I can't go more than n-1 edges, and I can say that okay, minimum spanning tree is formed now. And how can we check if they are forming a component? We can use DSUs, and this will get more clear when we are implementing the solution. Okay, so let's now move on to the code, and the problem that we are going to solve today is road reparation from the CSES problem set. And okay, so let's first read the problem statement. There are n cities and m roads between them. Unfortunately the condition of the roads is so poor that they cannot be used. Your task is to repair some of the roads so that there will be a decent route between any two cities. Now what is this line telling you? That there will be a decent route between any two cities, and we also want to, and for each road you know the reparation cost, and you should find the solution such that the total cost is minimum. If we want to minimize the cost, we want to repair minimum number of roads, and since we want to have a route between any of the two cities, it will form a tree. Okay, so this is clearly asking us to find the minimum spanning tree and actually find the sum of the edges of that minimum spanning tree. Okay, so let's see how we can code it. Okay, so what I will do is actually I changed my code editor from VS Code to Sublime because this one is much lighter for my machine. Okay, so these are the test cases. First we have, if we read the input format, first we have n cities, so I can say int n, c in n, I mean we have n cities and m edges initially, so c in n and m, and let's initialize a DSU of d of, let's say n+1 because I will be using 1 based indexing and not the 0 based indexing. Obviously I want to use my DSU template first. Okay, so this is my DSU template. Yesterday I forgot to add the code in the pinned comments, but today I did it. So you can go to the previous video, and in the description there will, in the pinned comment there will be this DSU code, and I will also add this code in the code below. Okay, so you can copy it from there. Now I have initialized the DSU, and in this DSU initially all the cities are disjoint, right? That is what we had in the Kruskal's algorithm. Now let's say for I in range m, we have three things: int, u, v, and w. U, v, and w. Right. Let's say c in u, v, and w. And since we are using Kruskal's algorithm, I should first store all these edges. So I can make a vector of I can do pair of pair int like that, or maybe I should just say array. Yeah, I think array will work. So let's say array of int and size will be 3, and let's say edges. Okay, and in this I will first add the weight. So let's say edges dot pushback. First thing that I want to add is the weight because when I sort it I want the weight to be minimum, u and v. Okay, so we have this now. Now what I'm going to do is I'm going to sort all these edges. So let's say sort edges dot begin comma edges dot end. Okay, so now when I sorted, since the first element was weight, so this will be sorted in the increasing order of weights. Now I have to keep two types of count. Let's say first is the count edges, so that will be 0, and int score, or you can also call it sum. doesn't matter. Now for in range m, I'm going to traverse in this whole thing again, and I will have and I will actually do two things. Let's make this a bool function, and if they were in the same set, let's say false, and I can here I can return true. So if I was able to join them, I will return true and increase my score. Otherwise, I will do nothing. So I can say if d dot merge what edges of I of 1 comma edges of I of 2, so u to v, if I am able to merge them, I will merge them, and my count will increase. So count plus plus and score plus equals to edges of I of 0. So that was the weight of that edge, and clearly I also need to break out of the loop. So if my count equals n minus 1, then I want to break it. Okay, now there are two cases, like if my count is equals to n minus 1, then I was able to make my whole minimum spanning tree, and now I will simply print the score of the minimum spanning tree. So I will say cout score and l. Otherwise I will have to print the impossible. I think it was written in here that I should print impossible. So cout impossible, right? Let's try to run this and see if it works. So we are getting some errors? Yeah, we are getting 14, which is the correct answer. Let's try to submit this and see if it is working. So this is the code, and let's see. Submit, choose file, code.cvp, submit. And the solution got accepted, and it runs in 0.11 seconds, so it is quite fast. And if you were able to understand this concept, kindly like this video, and if you have any suggestions, make sure to comment down. I will see you guys next time. Thank you.